Okay, so here are the chapter 3 solutions. So for problem 1, I've stated that in this question there's a 10 kilogram of R134A to fill a certain volume rigid container. Take note, it is a rigid container, meaning which is a fixed volume, at an initial temperature of negative 40 degrees Celsius, and then this container is heated until the pressure is 200 kilopascal. Determine the final temperature and the initial pressure. Right, so what's the first thing that we do? The first thing is we know of the temperature. Okay, so we head down to table A11 because this is for R134A and not water. So we head down to R134A table A11 and negative 40 degrees Celsius. The first thing we check is what's the saturated pressure. So this is 51.25. Okay, and the next thing is we check for saturated vapor values and the saturated liquid values. Okay, so over here we can see that we can write down the saturated liquid values over here, saturated vapor values over here. And then since we know that we know the volume over here, and then we know the mass over here, and then we can find out the specific volume. One specific volume is basically just the volume divided by the mass, and I get 0.1348. And then let's see this value. This value seems to be in between the saturated liquid and saturated vapor values. And what this means is this is a mixture of both liquid and vapor together. Okay? And then since it's in between these two values, this would mean that this particular state is occurring at this temperature and this pressure. Therefore, we know that the starting pressure will be 51.25 kilopascal. Okay? The next thing is realize that it's heated until 200 kilopascal. Okay, so over here from table A12 at 200 kilopascal, we can get the VF and VG values. Because it is a rigid container, this will mean that the specific volume doesn't change in this question, so it doesn't change from state 1 to state 2. So using these values, we compare with this VF and VG. What you realize is that your V, the specific volume, is more than the VG. And what this means that it has gone beyond the saturated vapor state already. It has taken a larger volume, and this will mean this is at superheated phase. Okay, so at superheated phase, you need to look at the superheated table. And that's when we know we need to go to table A13 to find out. So to find out, we realize that the specific volume is 0.1348. So we try to look at 200 kilopascal, where is 0.1348? It seems to be in between the temperature of 60 and 70. And then I can interpolate to find the temperature. Okay, so that's the temperature at the final state. So it's a very simple question. For next question, so there's a piston cylinder device contain 50 liters of liquid at 40 degrees Celsius and 200 kilopascal. Heat is transferred to the water at a constant pressure until the entire liquid is vaporized. Okay, so what's the mass of the liquid? First things first, we know that from table A4, because we have the temperature and pressure. So let's look at 40 degrees Celsius from table A4. We realize that the saturated pressure is 7.3851 kilopascal. However, 200 kilopascal, which is the initial state, is more than the saturated pressure. This would mean that the pressure is actually pressing the water molecules down. Okay, this would mean that it's nowhere near evaporating, and in fact this is a compressed liquid state. And then what we learned from the previous video is that compressed liquid is more dependent on temperature than pressure. Therefore, we can use the approximation to the specific volume as saturated liquid temperature. Okay, over here, so we know that specific volume, and I can approximate it at the VF at 40 degrees Celsius, and that will be 0.001008 meter cube per kilogram. Volume is 50 liters, which is 0.05 meter cube. Okay, so to find the mass, I can use the total volume divided by the specific volume and I can find the mass. Okay, simple question. Next, we can find the final temperature. So from at table A5, at 200 kilopascal, we can see the saturated temperature. And then we know that the saturated temperature we can find it out to be 102.21 degrees Celsius. So just look at table A5 and you can see the saturated temperature and you can find this. Okay, the next, total enthalpy change. So enthalpy at state 1 is basically enthalpy approximated at the saturated fluid at 40 degrees Celsius. Okay, and then we can see this from table A4. Like I said, this is approximate to the specific volume at saturated liquid temperature. Okay, sorry, is that saturated liquid temperature, because compressed liquid is more dependent on temperature than pressure. So state 1 you can approximate, then state 2 you can easily find from table A5. So what's the total enthalpy change? We just use state 2 minus state 1 times the mass of this liquid. Okay, and then you can find the total enthalpy change in kilojoules. If we plot the process on a TB diagram, we know that state 1 is compressed liquid, so it's somewhere down here, and then state 2 is right here. So the process goes from here to here. Alright, so that's for question 2. For question 3, a rigid tank which volume is unknown, so we don't know, but we know the ratio, is divided by one partition into two parts. Okay, so one side of the tank contains ideal gas, the other side is evacuated. Basically, there's nothing at all. Alright, so when you remove this partition, the gas will then fill up the rest of this container, but naturally the temperature would drop, because when the temperature drops, right, in this question it says that the heat is now reapplied to the gas until the pressure equals to the initial pressure. So first things first, let's use ideal gas equation, which is PV equals mRT. So we can bring the mass over, so PV over M equals RT, and this is also same as P times specific volume. Okay, so pressure 1 specific volume 1 equals to R temperature 1. And then we know that the volume is expanded to 3 times because this is V1 and this is 2V1. So you total add up is 3V1. So 3V1 is equals, 3V1 times P1 equals to RT2. But then when it reheats, supposed to be 3P2V1 equals RT2. But because you reheat until the pressure is equal to the initial pressure, that's why I replace P2 with P1 because it's the same. Okay? From here, you just manipulate the equation such that you can see that T2 over T1 has a ratio of 3. Okay, so just take note when you do this temperature, right, make sure you convert it to Kelvin. So basically T2 is just 3 times T1. So 925 degrees Celsius plus 237, I just convert it to Kelvin, multiply by 3, that's 3600 Kelvin. And you minus 273 and you get 3327 degrees Celsius, and that's the answer for question 3. For question 4, so for question 4, there's a spherical balloon with diameter of 9 meters is filled with helium at 27 degrees Celsius and 200 kilopascal. Determine the number of mole and the mass of the helium in the balloon. So this question is very simple. We know the most basic form of the ideal gas equation is PV equals nRT, where this R is a universal gas constant, which is 8.3145, but I put it as 8.314 close enough. And then I just sub in all the values that I have, and you can find out what's the number of moles, which is 30.6 kilomole. We know the molar mass of the helium is actually 4 gram per mole. Therefore, we can convert the number of mole into the mass of the helium, and then we find it out to be 122.42 kilogram. Alright, the answer is 123 in the textbook, but it's close enough. Okay. Next, for problem 5, this is the most interesting problem as we take note of the compressibility factor. So basically this question is to determine the specific volume of superheated vapor at 15 megapascal and 350 degrees Celsius using the ideal gas equation. So very simple, just use PV equals RT, this V is specific volume. You can very simply find the specific volume as 0.019167633. Okay, so very simple, you can find out very easily using one equation. Okay, next, generalized compressibility chart. So let's do this step by step. So we know that we are given the pressure of 15 megapascal and a temperature of 350 degrees Celsius. So let's take note of that. So how do we tackle this problem? First things first, let's make use of this Nelson-Orbit generalized compressibility chart. So trying to find as much reduced values as I can. So over here, I can find out the reduced pressure and reduced temperature, because I know for steam the critical pressure for steam is 22064 kilopascal from table A5. Okay, where you find the specific volume of fluid of the liquid is equals to the specific volume of the gas. Okay, and critical temperature for steam. Sorry, let me change this. Temperature for steam is 373.95 degrees Celsius. So from this, we can calculate the two reduced values. Using these two reduced values, I can approximate. So for example, reduced pressure is 0.6798. You can't really, so I can approximate to be 0.68 around there. So 0.68, I draw one vertical line upwards. The next thing is I know that my reduced temperature is 0.96298. Remember to convert to Kelvin. So 0.96298. So I'll look over here, which is in between. Let me see. 1, like reduced temperature equals to 1 and reduced temperature 0.95, somewhere in between. So I just draw one horizontal line and I find out my compressibility factor Z, which is equals to 0.65. Okay, so I approximate Z to be 0.65. I put into the formula to convert to put into the ideal gas equation formula to find out the corrected specific volume, which is 0.01245896. From what I can see, from what I can see from my answer, I'm not that far off, so my approximation is pretty good. Okay, so for most accurate way is to see steam table. So from steam table, we can see from table A6, we can find out that the specific volume is 0.011481. Okay, to calculate the error, very simple. I found out that ideal gas equation, the percentage error is 66.954%, which is massive. Okay, this would mean that because the temperature is relatively low, remember it's 350 degrees Celsius only. Okay, and then the pressure is also very high at 15 megapascal. Therefore, the percentage error is a lot more. And if you put into, when you use compressibility factor, you can see it reduces down the percentage error significantly from 66.9% to 8.5%. So that's how you do question 5. Okay, that's all for chapter 5.